Okay, numbers are picking up. Stop sharing the screen now. And, okay, I think we waited a minute. Maybe it's time to start now. Okay, so good afternoon, everyone. Welcome to today's NITheP colloquium. My name is Francesco Petruccione, and I'm the interim director of NITheP. Today, it is my big pleasure to introduce to you Professor Jeff Murugan. Jeff is a mathematical physicist based at UCT, and he also started his physicist career at UCT with a master's in mathematical physics. He completed then his PhD at University at Oxford University, and from there he moved on a series of postdoctoral positions at Brown University, at the Institute of Advanced Studies in Princeton, at the American Museum of Natural History in New York, and even at the ICTP in Trieste. And Jeff is, I think, by tradition and by training, a string theorist. But in recent years, he has discovered quantum information theory, and he has been working hard on developing connections between many-body particle physics, string theories, and quantum information theory. So Jeff, we are really very happy to have you with us this afternoon, and we are very much looking forward to your talk. And you're welcome to start sharing your screen. And while you do that, I will remind the participants to please make use of the Q&A facility to ask questions. And Dr. Sinaisky, who also you see at the top of the Zoom panel, will moderate the questions and answer session after Jeff's talk. So Jeff, please, if you want to start sharing your screen, you're most than welcome to start with your presentation.
Thanks, Francesco. Let me see if this works.
Yeah, seems to work.
Good. So let's hit the play button. Okay. I think this is now working. Let me move. Okay. Very good. Well, thank you, Francesco. It's a pleasure to speak in the NITheP colloquium. I'm glad that this series is working out so nicely in these very strange times we find ourselves in. And I want to talk to you today about scrambling and chaos in quantum networks. I have a byline here of things to think about when you can't fall asleep on planes. And I understand that that's maybe a little bit too soon for that joke right now. So let me change that and say things to think about during a global pandemic. So actually, my thoughts on this topic started on a long-haul international flight from Europe. And that's why I had the original byline. This is work that I've done in collaboration with my student, Jean-Gabriel Hartmann, who's now moving to France to start his PhD in many-body quantum physics. Dario Rosa, who's a postdoc at the Korean Institute for Advanced Study, and he's really collaborating on this work in progress that we have. And Jonathan Schock, who's a senior lecturer at the University of Cape Town, and really a close collaborator. But it'll also draw on some other work that I've been doing on many-body quantum chaos with Masaki Tezuka in Kyoto, and Chende Ma, who's a joint postdoc between UCT and the South China Normal University. Chris Lau, who's in Taiwan, and then some other work on one-dimensional or on 1 + 1 dimensional quantum chaotic systems and disordered systems in general. And this is work that I did while on sabbatical at the Institute for Advanced Study with Douglas Stanford and Edward Whitten. So what I'm going to be talking about today mostly draws on work in a paper that we published in January last year, and some work in progress that develops that. So the archive number is there if anybody wants to take a look at it. Okay, so the story I'd like to build really starts with the question, with a social question actually. And the question is, how connected are we really? So back in 1967, some social scientists, in particular a guy called Stanley Milgram at Harvard, and his group tried to quantify this social connectivity. And they wanted to make a precise question, so they wanted to quantify social connectivity in the United States. And they devised an experiment to do this. And this is really one of these experiments that becomes iconic as time passes. So the Milgram experiment worked like this. They would identify some random individual in Nebraska, and Nebraska largely because it's it's in the middle of nowhere in the United States, and a target individual in Boston, where the group was based in Harvard, in Cambridge, Massachusetts. And they would have the Nebraskans send a letter to the target. And the rule was you could only email someone, oh, sorry, you couldn't do this, this was 1967. The rule was you could only mail somebody this letter if they knew that somebody. So they had to get the letter to the target individual in Boston, and the rule was they could only mail somebody in their social network, right? So somebody that they knew and somebody that they thought would be better placed to connect to the target. And the question was, how many mailings, snail mailings, this took to get from the individual to the target individual. Right. So Milgram's team tracked the progress of this letter by having the participants send a postcard directly to the researchers in Boston when they mailed the letter. So they could tell which links were met and which links were broken by participants not actually participating in the experiment. Okay. What they found was really something remarkable. What they found was that, what they found was that with the relatively small variance, the letter reached the target individual by an average of 6 mailings. And the social network exhibited a small world phenomenon in that complete strangers were connected by a very short acquaintance chain, let's say. So I mean small world in the following sense. Imagine you go to a party in Alaska, say, and in this party you encounter somebody and you realize that the somebody comes from, I don't know, Potchefstroom. And the person that they were neighbors with in Potchefstroom happened to be your neighbor growing up wherever you were in Durban, say. So you look at this person and you go, ah, small world. Well, that's what I mean by small world. It's a short acquaintance chain that connects what seemed to be complete strangers. And what they found was when they studied the sequence of mailings and mailings of the postcard back to the researchers was that the connectivity in the social network was really mediated by a small number of highly connected study participants. Okay. All right, so this is social science. So what does this have to do with mathematical physics? Well, as a mathematical physicist, what I'm interested in is how to get a mathematical description of these problems. Okay, and this comes down to a branch of mathematics, which we'll talk about just now, called graph theory or network theory. So if this whole story is starting to sound a little bit familiar to you right now, it's because it probably is. Most of us these days have heard of 6 degrees of separation or Kevin Bacon number. And this is really popularization of this idea of small world networks. So what Milgram's team found was that individuals A and B in some connected network, as you can see here, were really connected by a short number of, a short acquaintance chain, in their case, an average of 6 acquaintances. Okay? So we say that A and B are separated by 6 degrees of separation. Okay. Well, it turns out that this concept is remarkably universal. And many systems, not just necessarily natural systems, but artificial systems as well, exhibit this kind of connectivity that we would call small world connectivity. So here's the internet, actually, organized by IP address. And what you see is pretty much the same structure. You see clusters connected by a small number of edges that stretch across the whole network. This is typical of a small world network. So this is the internet, the whole internet organized by IP address. Another example is perhaps the reason we're in this mess as we speak. This is the flight connectivity centered on Europe. And what you see is precisely the reason why today you can get, well, not today, but you know what I mean. In today's world, you can get from point A to point B anywhere in the world with an average of about 2 or 3 flights. And it's because we live in a hyper-connected world. We can transit this world relatively straightforwardly. So you look within the United States or Europe, you see a large number of interconnected cities with a small number of edges that connect these interconnected cities to everywhere else in the world. Okay, so this is flight patterns centered in Europe. Another place you might see it is in the human brain. Researchers at the University of Lausanne and Indiana University have begun a project to chart the connectivity of the brain, and showed that unlike the picture you see on the left, which is what we would call a large network, or a large world network, where lots of different neurons are connected to lots of other different neurons, actually the architecture of the brain seems to be more like the picture on the right-hand side, which is a small world network. So hubs, highly interconnected hubs, that are joined together by a small number of neural signals. And you can map this by using diffusion tensor imaging. And indeed, it seems like the human brain, the architecture of the human brain closely resembles such a small world network. Here's another picture that's really quite remarkable and rather pretty. And this is what we would call a collaborator network. So this is a collaborator network of people working in psychology, I think it is. But you know, as mathematicians or applied mathematicians, we're familiar with the Edish number, for example. In fact, people at KZN are particularly familiar with the Edish number. Given that Hender Swart was the doyen of graph theory at UKZN. Well, the point here is that every dot in this image, every vertex in this graph corresponds to a particular researcher in this field, and this researcher is connected to other researchers in the field by these edges. And if you take all of that information together and you visualize it, this is what it looks like. And you can see very similar structure to what you saw with the internet, or to what you saw with the flight paths based in the previous picture that I showed you. You get this highly clustered, clicky, neighborhood-dominated graph connected by a small number of edges. Okay, so small world networks are prolific in many different fields. And what I'd like to do today is give you a feel for what the underlying mathematics or physics of these networks are. But before we do that, we need to make sure we're speaking the same language. So I thought I'd spend a little bit of time and unpack some of the language that I'll be using going forward before things get a little bit too technical. And I must say, I like to give talks that are interactive. So if you have any questions, please do stop and ask, and I'm very happy to answer. I think it will be moderated by Ilya and Francesco. But please do stop and ask if there's anything that confuses you at any point. So let's start with a definition. So a graph or a network is a collection of vertices, so dots, and edges, lines that join these dots in a pairwise way. And the lines and edges are organized in a particular way, right? So for example, in these pictures that I have, you have 3 dots organized into a triangle connected by edges in a pairwise way, or you could have a single dot that's connected to multiple other dots. So that picture we'll call a hub. So you would say that the particular graph has a hub topology, or it could have a planar topology in the graph next door to it. There's a notion of centrality. Most of these ideas are quite intuitive. So if your intuition tells you what you think something is, it's likely that it's the case, and we'll go with that. So the idea of centrality is you have a node in a graph that's kind of center in the graph. It's not on an edge. It's not on the periphery of the graph. It's in the center. It's in the middle of the graph. Okay. And we'll define the notion of distance in the graph in a slightly more precise way just now. You can see in the last picture labeled 5 that there are various clusters that you can find in graphs and organize your graph in that way. So here we've got 3 clusters, and they're connected by single edges. And if you look at the picture, it's kind of obvious what a cluster should be. So on the whole, the organization of these networks or graphs can be regular, like a lattice, or it can be completely random, where I randomly connect vertices in a particular graph. A random graph is what we would call an Erdős-Rényi graph after its discoverers. And sometimes the topology of the graph can be of Erdős-Rényi type, or sometimes it could be a regular lattice that you might be familiar with. The organization can also be sparse or dense. And again, the definitions are intuitive, should make intuitive sense to you, right? And if every node in the graph is connected to every other node, we'll call that type of graph a complete graph. Okay. So let's make some of these definitions a little bit more precise. So here's an example of a graph in the center of the page, and you'll notice that my slides are organized in this kind of nonlinear way where there's something in the center of the slide, and then I build around this slide. I'd like you to focus primarily on the thing in the center of the slide, and let that be your takeaway for each of these slides. So typically it'll come in a yellow box. And that's the central message that I'd like to convey in a given slide. All right. So the degree of a node is the number of edges that are connected to that node, right? Now, associated to a particular graph is what we would call an adjacency matrix. This is a matrix of 1s and 0s, and a particular element in this matrix is a 1. Let's say the ijth element in the matrix is a 1 if there's an edge connecting vertex I to vertex j in the network. And this gives an unambiguous representation of any simple network. But what it also does is that it allows us to formulate network properties in terms of matrix algebra. And physicists and mathematicians and applied mathematicians love matrix algebra because I can take all of these abstract concepts and represent them in terms of a matrix, and I can represent their operations in terms of matrix operations. And I can bring to bear on the problem linear algebra, right? So in terms of the adjacency matrix, the degree of connectivity, the degree of a node is computed by basically summing over the column entries in a particular row, okay? So Ki is the sum of j of Aij. Now, given a matrix A, I can compute the spectrum of that matrix by diagonalizing the matrix and writing down its eigenvalues. The spectrum of an adjacency matrix in a network is particularly neat because it's a network invariant. And all I have to do to compute this network invariant is to solve the characteristic polynomial that I get when I compute the determinant of lambda minus a equals 0. Right? I can do more than that, though. To a given network, I can associate the idea of a Laplacian, a network Laplacian, and this generalizes the usual idea of the Laplacian that you might be familiar with as a second derivative operator. And this is defined to be the degree of a node I if I equals j, or -1 if I is not equal to j, but I and j but ij is a valid edge in the network, and it's 0 otherwise. And I can compute the network Laplacian by through the adjacency matrix by multiplying the Kronecker delta ij with ki, and then subtracting off from this the adjacency matrix entry. So Lij is ki delta ij, no sum on the I, minus aij. And what the network Laplacian is particularly good for is to partition the network in a particular way. And this is great if we want to, for example, compute the entanglement structure of a quantum network, where I need to partition the network into a set and its complement, and then study how those two are entangled with each other. All right. So let's give some examples of what the adjacency matrices would look like for particular networks. I should say that I've structured the talk to appeal to primarily the students in the audience. So for any experts in the audience, I would ask you to bear with me. I'll make it more technical a little later, but for now, I want to tell a story, and I want the story to be understandable to the young students in the audience. Okay, so consider the following two networks. Right? These are simple. Well, the one on the left is a simple network. The one on the right is not such a simple network because I have more than one edge connecting two nodes. But let's just deal with the one on the left for now. So here, the node 3 is a central node in the sense that it's central to the graph. There's vertices 1 and 2, and they're connected by an edge. This edge would be labeled 1, 2. And a typical node would be what you would see in 6, node or vertex. I use them interchangeably. Well, the same is true for largely for the network on the right-hand side, except that node 6 has an edge that connects it to itself. This is what we would call a self-edge. Nodes 1 and 5 are connected by 3 edges. So this would give you what we would call a multi-edge. And sometimes we would take this multi-edge and we'd squeeze them into one thicker line and denote that appropriately in the adjacency matrix. So the adjacency matrices for both of these graphs can be written down, and they look like this. And you can see that the adjacency matrix for the graph on the left-hand side just consists of 1s and 0s. Okay, it's defined as we defined it in the previous slide. The adjacency matrix on the right-hand side is slightly different from what I defined in the last slide because I've got 2s and 3s. And this corresponds to the fact that I've got thicker edges joining particular nodes, which I can split out into multi-edges. Associated to the first adjacency matrix, I can go ahead and compute its network Laplacian. And as you would expect, the network Laplacian is a matrix-valued object as well. Okay. So let's define the notion of distance. And as you would expect, distance really measures how long it takes you to get from one node to any particular other node. So the distance between nodes 1 and 2 on this graph, I'll denote by d12, this is 1. I have to traverse one edge in order to get from 1 to 2. On the other hand, to get from 1 to 3 along a particular path, d13 is 2. Okay. And this is the smallest distance between 1 and 3. I can, of course, find other routes that take me between 1 and 3, but those will all have greater than or equal to distance 2. Similarly, d14 is 2, d15 is 1. Given what this shortest distance between any two nodes in a particular graph is, I can calculate the mean distance between any particular node and all the other nodes. So the mean distance between node 1 and all the other nodes I get by adding d1j for j going from 1 to 6 and then dividing by 6, so I average over that. And that's 1.5, so 3 halves. So the mean distance between node 1 and all the other nodes is 1.5. Similarly, given L1, L2, L3, L4, L5, L6, I can average over the entire network, and then I get the mean distance between nodes for the whole network, which really is a measure of the connectivity of the network, to be 4/3 in this case. Okay. Then there's the idea of clustering. And the clustering in a network is a measure of how two nodes are related in some way. So here's the same graph, and take nodes 5 and 6. So you can see that nodes 5 and 3 are related, and nodes 3 and 6 are directly related, but nodes 5 and 3 are not directly related. So in a social network, we would say that the friend of my friend is not necessarily my friend. Okay, so all of these things that I'm talking about in the networks, you can kind of picture what happens in a social network like Facebook. On the other hand, if I take nodes 2, 3, and 4, then I see that nodes 2 and 3 are connected and nodes 3 and 4 are connected, but so then is nodes 2 and 4. So while the friend of my friend is not necessarily my friend, the friend of my friend is likely to be my friend. Again, think in terms of a social network like Facebook. Okay, so now we need a couple more definitions in order to talk about small world networks. One of them is loops. So paths of length 2 and that are closed form loops. And a network with a lot of loops, with a large number of loops, is what we will call a clustered network. Okay, so these are self-contained little units within a particular network. And here you should think about, for example, in a given city, let's say neighborhoods in the city, or amongst a given group of friends, cliques in the group of friends. Okay. What we would want to do is to quantify the clustering in a network. And this can be quantified by what we call the clustering coefficient. And to calculate the clustering coefficient in a particular network, what you do is you count the number of closed paths of length 2, and then you divide it by the total number of paths that have length 2. And if you think about it a little bit in simple networks, you realize that that fraction is the same as the fraction that you get by counting the number of triangles, because the fundamental closed loop in a network like this is a triangle, multiplied by 6. And I'm going to leave this as an exercise for the students to think about why 6, and then divided by the total number of paths of length 2. And for similar reasons, this is the same as 3 times the number of triangles divided by the number of connected triples. Okay, so connected triples are not necessarily closed; they're just any 3 nodes in the graph that are connected. Okay, so graph theorists know all of these things in second year already, no doubt. I'm not saying anything particularly fundamentally deep in this. It's just a question of combinatorics of graphs and how you organize and quantify their properties. So now I want to talk about small world networks. Okay, a small world network is a graph that has very particular properties. One is that the typical distance between any two randomly selected nodes on this graph is short. So it's easy to get from one point in the graph to another point in the graph. So the typical distance between 2 randomly selected nodes is small. How small? Well, it scales like the log of the number of nodes in the network. But this is not the only property, because certainly random graphs have this property as well. What distinguishes a small world network from a random Edish-Renyi type network is the fact that there's a large degree of clustering in the network. So in addition to the typical average distance between 2 randomly selected nodes being small, it's also a highly neighborhood-dominated graph. It's highly clicky. So if you want to think about, if you want something to visualize, you should go back to the picture that I showed you about flight paths in the world. Well, the world is organized into countries, and countries are organized into provinces, and provinces are organized into counties or suburbs, and suburbs are organized into neighborhoods. And people in the neighborhoods tend to interact with their neighbors more than anybody else. And people in provinces tend to interact with people in the same province more than people in other provinces. And people in countries interact with people in their own country significantly more than they interact with people in a different country. This is what I mean by neighborhood dominated. So there's a lot of cliquey interaction in the world. And prior to international travel being relatively easy, let's say prior to the early 1900s, the world was really a large world. It took you a long time to get from any particular point in the world on the globe to any other point on the globe. But with ship travel and plane travel today, it really doesn't. Okay, so the world is small in the sense that even though there's a large degree of clustering in the world, there's a large degree of interacting within neighborhoods, the typical distance between two randomly selected neighborhoods in the world is generally short, and in fact it scales somewhat like log n. So small world networks interpolate between the clustering properties of a regular graph, a lattice, and the rapid spreading of information that you get in a random network. Okay, and it's precisely this interpolation that make them so valuable. So how do we measure how small world a particular small world network is? Well, one way to do it is through something called the smallness coefficient. And the smallness coefficient is really a measure of how such a network, how such a small world network compares to the associated network with completely random connections. So in this case, CR and LR are the clustering coefficient and the typical path length of the associated random graph. So imagine I take a particular network, which I said is made up of nodes and edges, and I draw dots for each of the nodes. Right? So I have a small world network, it's got a particular connectivity. I then make a copy of this network, delete all the edges, and then randomly distribute the edges amongst the same distribution of nodes. Then I'll get the associated random graph. That graph will have some clustering coefficient and some path length, which I will call CR and LR. So then to calculate the smallness coefficient, what I do is I calculate the ratio of the clustering coefficient of my graph to the associated random graph. I calculate the path length of my graph to the associated random graph, and I find the ratio of those two. If that number, sigma, is greater than 1, then I have a small world network. The problem with this as a measure of small worldness is that it's very dependent on the network size. And when the network size gets to be too small, then this becomes quite an unreliable measure, diagnostic for small worldness. There are other parameters that parameterize how small world a particular network is. One of them is what we would call the small world parameter, omega. And omega is 1 minus the absolute value of LR over L minus C over CL. This number, it turns out, ranges between 0 and 1. Well, this is great. And it's also not particularly sensitive to the size of the network. Because it ranges between 0 and 1, I can think of it as a tunable parameter to take me between a lattice, where omega is 0, and a fully small world graph where it's equal to 1. Okay. So I said that the typical distance in a small world graph scales like log n, and that means that this typical distance is small, even though it's got a large degree of clustering. I can go on further and come up with what are called scale-free networks. And scale-free networks are a very special class of small world networks that are proliferated by a large number of hubs in the system. If you remember what I said earlier, a hub is a node that is connected to a large number of other nodes in the network. Well, scale-free networks have a large number of these hubs in the network. And as a result, the mean path length is significantly shorter. And in fact, this thing scales like the log of n. Okay. They have some rather remarkable properties and are quite popular in epidemic modeling, which I will come to in a little bit. So how do you make a small world network? Well, this is one of the truly remarkable papers in the scientific literature. It's a paper by Duncan Watts and his then PhD supervisor, Stephen Strogatz, who's an applied mathematician, award-winning applied mathematician at Cornell. So they were interested in trying to understand synchronization in nature. And in doing so, they came across an interesting algorithm, which I'm going to call the Watts-Strogatz Protocol, for producing such small world networks. And it goes a little bit like this. It says, start with a regular n-node lattice. So I have n nodes in this thing, and it's a lattice. So basically, let's say nearest neighbor connections or next to nearest neighbor connections, or in general, some k-local connections. It doesn't really matter. But the point is that it's a regular lattice, okay, with some degree of connectivity. So in the picture in the center, the ring on the far left of that picture is the regular lattice, okay? And this lattice will have, let's say, k/2 nearest neighbor edges. So what you do to make a small world network out of this is you go and visit each node, call it ni, okay? So at node ni, you iterate through each edge, ij, connecting ni to nj, where nj is not the same as ni. And then with some predefined probability p, you delete that edge and you rewire it by joining ij to some random ik. Okay? Well, as you do that and you increase the randomness p, you will go from left to right, from a regular lattice to a completely random lattice, an Edish-Rayleigh network. And somewhere in between, in fact, as soon as you transit out of the regular lattice, you're in a small world network. And you can see graphically what a small world network is. It's a network that has a large number of triangles. And these are spherical triangles, but be that as it may, it's a large number of triangles. So it's a highly clicky, highly neighbor-dominated graph. But in and amongst those n nodes, n lattice points, you have some small number of nodes that can travel across the entire network. But this is why we live in a small world. Because even though most of us, on a daily basis, interact largely with people in our neighborhood, a small number of us can actually travel across the globe. And it's us traveling across the globe that make it a small world. And it turns out that even having order 1 in an order n lattice, having order 1 edges that stretch across the entire network make it a small world network. Okay, so this network inherits all of the clustering properties that come from the underlying lattice, as well as the long range, as well as the short path length that it inherits from the associated random graph with long range connections. And it's this great hybrid in between with this dialable parameter omega, that, or in this case p, the probability of rewiring, that allows you to interpolate between these two. Okay. So here's an example of various lattices. In the top row, p equals 0 means we have regular lattices. Remember I said I wanted these to be k/2 connected lattices. So k equals 2 means each node is connected to its neighbor on the left and its neighbor on the right. K equals 4 means it's connected to its neighbor on the left and the right, as well as their neighbors, their immediate neighbors. So this is a next to nearest neighbor lattice. And then k equals 6 on the far right. And then as you go down, I'm turning up the rewiring probability. And you can see that the graphs are slowly getting more and more random looking. They're still closed, they're still rings, but they go from being lattices to completely random, well, not completely random, p equals 0.9 on the bottom row. Okay, and this is the Watts-Strogatz Protocol. It tells you how to build such small world networks. Okay, and then I can go ahead and calculate the clustering coefficient and the path length of these networks in the same way that I said earlier. Ah, sorry, there was one thing I wanted to tell you about. Okay, so the picture on at the bottom there is a plot on the same axes of the degree of clustering versus the path length through the network as I turn up the probability. So it's plotted as a function of the probability P that goes from 0 to 1. And what you can see is that as you transit, the path length drops off rather rapidly. So this is the orange curve. So as you increase the probability of rewiring P, the path length drops rapidly, whereas the graph remains largely clustered in the blue curve, and then only toward the end, as you approach a random network, does the degree of clustering go down. And that entire hysteresis type S-shaped blob in the center constitutes small world networks. And what we would call a maximally small world network is the one that has the biggest difference between the blue curve and the orange curve. So why are these interesting, except if you want to think about Facebook? Well, like most of you, I spent the last couple of months in lockdown with lots of time and a growing interest in epidemiology. So I decided to spend some time and try and learn a little bit about epidemiology, to try and understand what it is that the scientists were telling government and what government was telling me and how much of that I could trust and all of that stuff. And so I spent some time learning about standard epidemiological models. So traditional epidemic models take a population and they compartmentalize the population into various compartments whose interaction they can then study through some differential equations. And if you can solve those differential equations, then you can build models. And if you can build models, then you can try and understand how a virus spreads, for example. So the most popular such models are what's called SIR models. So these models break the population into susceptible, infectious, and removed populations. So susceptible populations are people in the population that can get a particular virus. The infectious are people that have got it and are able to transmit the virus. And then removed population groups are either immune, having got the virus and gotten over it with antibodies, or dead. And we won't distinguish between the two. You can, that gives you another class of models, but we won't. So it should be clear from your first or second year courses in applied mathematics that the number of susceptible individuals grow in proportion to how many people are infected, how many people are susceptible, as well as how many people are infected and they can catch it. So S dot, and these are normalized variables, so I normalize them by dividing by the total population. So S dot is proportional to minus Sx, and the minus sign comes because the susceptible population is decreasing as more and more people get infected. And the proportionality constant I will call beta. And if S dot is minus beta Sx, then X dot, the number of infected individuals, a fraction of the infected population, must grow like beta Sx. But if some percentage of that population is being removed from this set by either dying or becoming immune to the disease, then I have to subtract off something proportional to X. So let's call that gamma X. And then similarly, the number of removed individuals must grow like gamma X. So R dot is gamma X. And all of these differential equations must be subject to the constraint that S plus X plus R must be 1 because this is a normalized population. So this is a basic SIR model. And one way to execute a sanity check on this and check that you're getting everything correct is to set gamma equals 0, so you don't remove the population, you don't remove any part of the population. And this reduces an SIR model to what's called an SI model. And an SI model is what you would normally call a logistic model. So here the model grows with the X, the number of infected individuals, grows logistically. And you can solve this exactly, and you can write down the solution. And the key point about SI models is that there's always an epidemic. As soon as you go away from X equals 0, it will just keep growing, and you can see it grows exponentially. So there's always an exponential, there's always an epidemic in an SI model. So what about an SIR model? What happens if we turn on gamma? Well, sorry, before I do that, here's the plot of X as a function of T, and you can see this logistic curve that everybody knows and loves from first year already. What about an SIR model? Well, in the SIR model, you can solve it as well, but you can't solve it exactly because you can't do the integral. So you can write it down as, you can write down the solution as a quadrature, as an integral, which needs to be solved. And even though you can't write down an exact closed form solution for that integral, the integral from 0 to r of du over 1 minus u, blah, 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 what you can do is you can analyze it asymptotically. So in particular, at late times, when t gets very large, you can see that r, the number of removed individuals, goes like 1 minus e to the minus beta r over gamma. And you can see that there's actually a critical point in this model at beta equals gamma. And this defines an epidemic threshold. So unlike the logistic model, where you always had an epidemic, in the SIR model, sometimes you don't get an epidemic. You don't get an epidemic precisely when beta is less than gamma. So when gamma is equal to beta, then you get an epidemic. So this gives you an epidemic threshold. You can do more. You can calculate this R number that everybody knows and loves by now, this basic reproduction number. And in this SIR model, the basic reproduction number is just beta gamma times that integral with the particular assumption for the distribution of the population. Okay? And it's beta over gamma. So these two parameters, beta and gamma, really control everything about these models. And if you numerically solve for S, X, and R, you find precisely these curves that we've been seeing over the last couple of months. In particular, the infected curve is precisely the curve that everybody's been asking us to try and flatten. Okay, that's where it comes from. I'd like you to pay attention to two things here. Unlike the SI model, which looked like that, and not only did you always get an epidemic, at some point, everybody in your population got infected. That's why the curve goes up to population size 1. Here, on the other hand, not everybody gets infected. So there's two things to keep in mind. One is the number of susceptible individuals doesn't necessarily go down to 0. And that's because in an SIR model, there are some lucky individuals who will just not get infected with the virus. On the other hand, the number of recovered individuals doesn't necessarily always go up to 1. So these are basic facts that most epidemiologists know and are very familiar with. The issue that I took with a lot of these models that were coming out was a lot of them, at least the most naive ones, included this assumption that the populations interact in a fully mixed way. This is not a very realistic assumption. So what happens if you try and break that assumption and have or rather, how would you try and break that assumption? How would you try and model a population where the interaction is not homogeneous? It turns out that a really good way to do it is to put this SIR model, instead of doing it on a continuum, you put it on a lattice. You put it on a graph, on a network. And in this setting, a uniform probability of interaction corresponds to a random network. But real social networks are not random. Typically, they exhibit clustering. Two people are more likely to know each other if they have a common acquaintance. The friend of my friend is more likely to be my friend than not. But I'm not connected to any random person I'm less likely to be connected to any random person in the network. And this builds into the problem two important epidemiological parameters, that of susceptibility. How susceptible is a population to a particular virus? As we learned over the last couple of months, older individuals in a population are more susceptible to catching the coronavirus than younger individuals in the population, children in particular. And secondly, the transmissibility of the disease. How transmissible is the disease? How easy is it to spread this particular disease? Some diseases spread much easier than other diseases. So these two epidemiological parameters, transmissibility and susceptibility, are very, very important in building any of these models. And when an epidemic takes place on a network, can be mapped to the problem of percolation in a small world network. Now, I must be honest, I didn't really know too much about percolation until I started thinking about these types of problems. I mean, I knew that my coffee percolated, and I knew that there was some idea of percolation in our energy physics through Coleman's work, but I didn't really pay too much attention to it. But this is a hell of a fun thing to think about. So let me spend a few minutes to just talk, tell you about percolation for those of you who are not familiar with it. So here's the standard defining experiment that was used to understand percolation. So imagine I have a grid, and this grid is chicken wire, right? So chicken wire, I have a grid like this, and I connect one end of the grid to the battery and the other one to an ammeter, and I make a closed circuit. So it's a metal grid, and each of the connections, the 4-point connection there, I denote by a dot, right? Sorry, just let me see if I can move this. Yeah, let's try this again. Okay, so the story is the following. So now I'll take this chicken grid, and I see that there's some current flowing in the circuit. Great. This is a 137 by 137 grid. And I cut some of the wire. And I cut them, and I denote that cut piece of wire by an open circle surrounding those nodes. Okay. And I can calculate the ratio of unblocked sites to, or cut sites to the total number of sites. In this case, the total number of sites is 137 squared. And I measure whether the electricity still flows. So yeah, sure, the electricity finds some path here, and it'll go from one side to the other. And then I cut more, and I cut more, until the electricity stops. The smallest value of phi, the ratio of cut sites to the total number of sites, at which no current flows through the grid, is what we will call the percolation threshold. At that point, there is no path, even though the chicken wire is not completely disconnected. Oh, I should say that when I cut the grids, I cut them at random. I can label each of these nodes by some number, put all the numbers in a hat, and then randomly pick out numbers from the hat and cut that node, right? So I randomly cut the node. I randomly remove that node from the network, and I test whether there is a path from the one side to the other side. And the smallest value of phi at which there is no path across is called the percolation threshold. And then one really interesting property that was found of this particular experiment is that if you run this experiment many times in what we call many realizations of the system, you will find that the percolation threshold is a constant of the system. Okay, so that's percolation. Well, what does this have to do with small world networks and all of that? So you can study this problem numerically. You can take this SIR model, you can put it on a small world network, and you can solve the system numerically. And much of what I'm going to say now sounds completely common sense, but this was the first time that it was actually quantified in epidemiology. In particular, it was shown that epidemics spread more rapidly in highly susceptible populations. The amount of time for an epidemic to spread is given by the average radius of connected clusters of susceptible individuals. So I had susceptible individuals, they interact in a cluster. The average size of that cluster determines the amount of time for the epidemic to spread. And the infection curve flattens as you increase the percolation threshold. So if you really wanted to flatten the curve, and that's the picture in the bottom there, if you really wanted to flatten the curve, then what you did was you made it harder and harder for the virus to find a path through the network. So the key thing about this is that you're not controlling properties of the virus. Neither are you controlling properties of the individuals in the network. You're controlling the topology of the network. And by controlling the topology of the network, it turns out that you can actually halt the spread of the virus in the network. So this was a remarkable thing. And in particular, you can show that, that there's absolutely no epidemic outbreak below the percolation threshold. So the percolation threshold allows you to tune in a particular network by tuning the topology of the network, how rapidly the virus spreads. All right, so that's a slight aside on something that I got interested in the last couple of months, kind of porting what I was thinking about in quantum systems to epidemiological modeling. So let's get back to the quantum system that I wanted to talk about. And the system that I wanted to talk about is what we were calling a quantum small world model. We built out of the Hamiltonian for a Heisenberg spin chain. Right. So here I have a network, and every vertex in the network, every node in the network is the site of a spin half state. So there's a spin, it's either up or it's down at every node in the network. And the edges in my network represent spin exchange interactions between these states. So I have a spin up and spin down at this point. If I exchange those two like that, that represents, if it's possible to exchange those two like that, then I have an edge connecting those two sites on the lattice. The S's are the Pauli spin matrices that represent the spins at each site. And the network topology is, as usual, encoded in the adjacency matrix Aij. You can see in the Hamiltonian. And again, this is either ones or zeros if we normalize the couplings. So here's a picture of what that looks like. So on the left-hand column, you have the actual network. We use an 11-node quantum network, an 11-node spin chain. In the middle is the adjacency matrix, which has been coded black or white. It's 1 for black and 0 for white. And you can see the structure of the adjacency matrix. On the right-hand side is the numerically diagonalized eigenvalue spectrum of the Hamiltonian. Right. For nearest neighbor interactions, this is the standard XXX Heisenberg spin chain, which is by now well known and much loved, and it's an integrable system, which means I can solve it completely. But even for more general couplings, as long as the couplings remain regular, in other words, I'm still talking about a lattice, even though the system is not generically integrable anymore, I can still solve the eigenvalue problem because it means diagonalizing some 2 to the n by 2 to the n matrix of complex entries. I can do that, at least, brute force. What we wanted to do was take that Heisenberg spin chain and make it into small world spin chain. And again, by implementing the Watts-Strogatz Protocol for, let's say, k equals 4 and an 11-node lattice, from top to bottom, the only difference between these chains is the rewiring probability. Remember, what we're doing is we're going to each site, and with some probability, we're deleting some edge, and we're rewiring the lattice. That's how you go from the top to the bottom. And what you can see is at the level of the adjacency matrix, you start off with a relatively ordered adjacency matrix, and it becomes more and more like a crossword as you go further down, reflecting the fact that now I'm going in increasing degree of disorder. And we asked the following question. We asked, how does this network scramble information? Okay. So the overall question we would like to answer, we'd like to understand here is, how do quantum small world systems, how do quantum small world networks scramble information? So first I need to tell you what is scrambling and how you measure such scrambling. So scrambling is the tendency of any many-body quantum system to spread the information, to delocalize the information over all its degrees of freedom. Okay, and I can consider this with a closed system. Okay, so this is not a system that I can model as an open quantum system, say by coupling to a bath, in which case I stick in some energy and I watch that energy disperse as carried away by the bath. This is a closed quantum system, and this is many-body delocalization. How do you diagnose this? Well, one way to do this is by what we call the thermally averaged commutator squared. I'm going to call this C of t. So basically, I find some operators in the system, I calculate their commutator, I square that commutator, and then I take the thermal average of that commutator squared. If you expand this square commutator, then an equivalent way to calculate this, what we call out-of-time ordered correlator, is the 4-point function that you see there. A dagger of t, b dagger of naught, A of t, b of naught. And you'll notice that unlike the usual kind of correlation functions that you would compute in quantum field theory, where you have a time ordering that orders your operators in increasing order of time at later and later times, here I go from t equals 0 to t equals t, back to t equals 0, back to t equals t. So this is an out-of-time ordered correlation function. And the out-of-time ordered correlator computes for you the degree of scrambling in the network. It tells you how information is spread over the degrees of freedom in the network. So what we did was we took the Heisenberg spins in the, promoted them to the Heisenberg spins in the Heisenberg picture by acting on them from the left and the right at the time with the time evolution operator, e to the IHT or minus IHT. And then sandwich them between some pure states, let's say psi. And that computed for us at particular beta the 4-point out-of-time ordered correlation function. And my claim is that this is a good diagnostic for how the system scrambles information. It's not the only diagnostic that I could use. Another thing I could try and calculate is what's called the spectral form factor. And the spectral form factor is nothing but the analytic continuation of the thermal partition function of the theory. So the partition function is something we normally denote by Z. It's a function of beta. Beta is the inverse temperature. Well, this asks me to take that Z, analytically continue it to imaginary time, to write down some Z of beta t, take the modulus squared of that, and divide it by Z of B. And then I average over the many realizations of this disordered system. So the angle brackets there with the subscript J is a statement that I need to average over the disordered, over the disorder of the system. Okay, now, there are two different ways I can calculate this thing. It depends on how I choose to do the averaging. Either I could take mod squared of Z divided by Z and average over the whole thing. This is called the quenched average. Or I can calculate the average over Z squared over mod Z squared divided by the average over Z squared. Sorry, the average over Z squared. That square should be inside the average. In which case I have what's called the annealed spectral form factor, or the annealed average. It turns out that in the large n limit, when our system gets very large, the difference between these two is negligible. And for computational purposes, it's easier to calculate the annealed spectral form factor that you see in front of that you see there. So that we'll call G of T and beta. Well, the neat thing about the spectral form factor is that in a chaotic system, right, in a system that is truly chaotic, truly quantum chaotic, if I leave that system long enough, then effectively it becomes, eventually it will become a random, it will exhibit random matrix theory behavior. Okay. And random matrix theory is something that goes back to Wigner a long time ago when he was studying highly excited atoms. And there's lots of measures for how to study random matrix theory. But these are all like statistical measures. And we were trying to come at it as from field theory. That's why you would calculate the OTOC. Well, the spectral form factor is nice because it exhibits similar random matrix theory type behavior, but is a quantum field theoretic quantity, and it's closer to the OTOC than these statistical measures. So you can go ahead and you can calculate the spectral form factor. So here's a plot of the spectral form factor, sorry, of the OTOC for the spin chain, where I insert at spin 1, at site 1, I insert some energy and I watch that energy propagate through the system. And the reason it's coming back is because it's a chain. So the energy goes around the chain and then comes back like that. And then we turn up the disorder in the system. We make it more and more random. And what we saw, what we were trying to understand is whether this was just scrambling or whether we were making the system chaotic. If you have a chaotic system, then the OTOC exhibits exponential growth. And what we saw here was that the OTOC was not going like an exponential. It was actually exhibiting power law growth. It goes to C of t goes like t to the some b, where b was somewhere between 1.76, or let's say 1.7, and about 3.4, 3.5, say, right? Depending on the degree of randomness in the system. So this is great because it's telling us that even though the system scrambles information, the folklore that's currently popular is that scrambling and chaos are the one and the same thing. Well, we're seeing something that's not chaotic. This is not a chaotic system, but it's still scrambling information. It's just doing it in a power law fashion. To back this up, we thought, well, let's go calculate the spectral form factor, because we can certainly numerically at least calculate the partition function for this system, and we can do the numerical computation of the spectral form factor. So what would you expect to see for a spectral form factor in a scrambling system? You would expect to see a particular type of behavior that we call a dip. The spectral form factor starts off, it then dips. Then there's a linear ramp, and then it plateaus. Okay, so we were seeing a dip ramp plateau behavior, provided we averaged over a large enough number of realizations of the system, which indicated that yes, indeed, this was a scrambling type behavior. This is a very nuanced picture that I don't have time to go into, but the upshot is that if I average over sufficient realizations of the system, I start to see precisely this kind of dip ramp plateau behavior that you're seeing in the rightmost figure there. Okay, how much time do I have?
Sorry, Jeff. Yeah, we are almost there. Yeah, okay. Usually we try to keep it to 1 hour.
All right.
Yeah, but
I can stop then.
No.
So let me go to,
yeah.
I can go to the, all right, so there's a bunch of other things that we can do that have to do with the spectral statistics of this problem, and this is the work in progress. But I think let me end by telling you a little bit about what we've studied and where I think this could be important. Okay, so what we found is these quantum small world networks offer a rather interesting and novel class of many-body problems. And why it's interesting and why it's novel and why I'm interested in it is because it gives us a way to parametrically interpolate between integrable systems, which are regular lattice-like systems for, let's say, the Ising model or the Heisenberg spin chain, and chaotic, completely random systems. And now we have a dial that allows us to move from the one to the other. So what we're hoping to study out of this is how quantum systems transition into chaos. How do we start with an integrable system and watch it evolve into a chaotic system? Not dynamically, but parametrically. However, there are many things that we still wanted to understand. In particular, these diagnostics, the spectral form factor and the out-of-time autocorrelator. These are diagnostics that are best. They're tools that come into their own in large N systems. So, for example, one very popular large N system right now is what we would call the Sachdev-Kitaev model in quantum many-body physics or string theory. That is, from the high-energy physics point of view, supposed to be the dual field theory to a two-dimensional black hole. Not the space-time around the black hole, but the black hole itself. And from the condensed matter system, this is a system that exhibits an incredible amount of physics, from maximal chaoticity to spin glass physics, which is what Sachdev and Yi were studying back in the 90s when they came up with the model that Alexei Kitaev modified. So the Sachdev-Kitaev model at large K and large N is one such model where the OTOC and the spectral form factor actually give you good diagnostic control over the theory. However, the systems that we've been working with, even though they're quite simple, there's just the Heisenberg model and the Ising spin chain, have to be numerically computed and understood. And our numerics, for computational reasons, are restricted to values of k, the locality of the spin chain, being less than n, the number of nodes in the network, being less than 11. So technically, we don't have a large n many-body system. We have a few-body sparse quantum system. So we really need to better our numerical tools for understanding these systems at larger values of n and k. One way that we're tinkering with at the moment is to use neural networks to try and probe these systems, because they don't have the same computational constraints that we do using standard many-body tools. And that's something that we're thinking about at the moment with Dario. The next significant limitation that we have is that our computations are really restricted to some very simple infinite temperature limits, especially when we want to calculate the spectral form factor. So this is by setting beta equals 0. Beta, remember, was the inverse temperature, so beta equals 0 is the infinite temperature limit. Well, in these systems, finite temperature corrections are really quite important. And partly this is because one of the conjectures that we're trying to understand is the conjecture that quantum chaotic systems are bounded by how chaotic they can become. In other words, the measures on quantum chaos, like in particular, the Lyapunov exponent, is bounded by the temperature of the system. So in our system, the Lyapunov exponent is infinite because the temperature is infinite. But in a system where there's a finite temperature, then we'll actually be able to see whether how chaotic a system is, like this, is really bounded by this what we call the Modesena-Schenker-Stanford bound on the quantum Lyapunov exponent. And then finally, I want to end off by making the following speculative statement. So this is clearly a toy model. I don't pretend that it's not. But the physics of this toy model, this interacting spin chain or interacting Ising system, is not unlike recent tabletop cold atom experiments in cavity QED, where the interactions between the spins is mediated by some laser in the cavity, in the QED cavity. And those models are really quite well. They're one class of models that people have been using to do quantum computing. In fact, these are the defining type of quantum computing systems in ionic quantum computing, for example, what IonQ uses for their quantum computing protocols. And so, while this is a toy model, perhaps it might be useful, perhaps it might show up again in the study of these ionic quantum computing systems in tabletop cold atom experiments. So it gives me hope that I come from a string theory community and I might actually be thinking about real life systems. And with that, I would like to thank you for your attention.
Yeah, thank you very much, Jeff, for a fascinating talk and for sharing with us this interesting journey from graph theory over epidemiological models to quantum chaos, many body models, string theory, and quantum computing. So a really fascinating journey. So thank you very much for that. Ilya, are there some questions that the participants would like to ask Jeff?
There is, in fact, a question from anonymous attendee, and it's related to the very beginning of the talk. And that's related to the experiments on the degree of separation. And the question is the following. This experiment reports statistics only on the successful streams of letters to targets. The number of letters that didn't reach the target at all was far greater than ones that did reach the target. And this was uncounted for in this 6-degree separation experiment. Is this true?
Not that I know of. In fact, the experiment was repeated in a more modern context of emails, and I think that the average number of mails that it took was also around 6.
Okay, thank you. There is no more questions in the Q&A facility, and if somebody wants to ask questions, people can just raise their hands and we're going to give them a right to talk.
And Jeff, maybe while people think about questions, have you already looked into running some simulation on the IonQ quantum computer or not yet?
Not yet. This is something that I'm very keen to do, actually. Have you guys done anything?
Not on the IonQ. We've used many others, but nowadays, since I guess since a month or so, the one IonQ computer is in the Amazon cloud. So for money, it is accessible.
Right. And that's interesting. I mean, so Dario and I were thinking about we're thinking about this neural network computation to study essentially the localization delocalization transition in these kinds of networks, and we figured we would probably need better computation than we currently have, but it would be fun to learn about using the quantum computation to do it.
Yeah, okay, that's cool. We can speak about it in a separate setting and see what we can do, because we are also looking now into playing around with IonQ. You know, we just need to find a way to pay Amazon. Yeah, but that's just a financial technicality. Yeah.
Yeah. I mean, this wasn't in our thinking here was not so much to use IonQ's quantum computer, but to understand properties of the IonQ quantum computer and to see if we can, make it efficient, because you don't need to have, the point here is that you don't need to have an all-to-all interacting system to have these properties. You can still have your nearest neighbor or next to nearest neighbor or some finite k local interaction Hamiltonian, and then just give it order 1 or so long range interactions, and so you still have much of the properties of the random network system.
Okay, no, that's very interesting, because I mean, other quantum computers have other architectures and other connectivity, so it could also be interesting to play around with that.
Yeah,
we should talk some more with Dario.
Yeah, that would be very nice. Yeah.
Of course, the advantage of the IonQ is that it's truly fully connected. With all the rest, you have a limitation of topology, and in the moment when you want, have a not neighbor-neighbor connection, you begin to lose your coherence very quickly.
That's right. That's correct. So that gives their system stability, is that they can maintain a coherent connections.
Yeah.
But from the point of there is a question. Okay, so what kind of interaction is taken into account in the XXZ model? Is it nearest neighbor or next to the nearest neighbor?
So typically the XXZ model is nearest neighbor as well. You just change the spin of the Pauli. But you can certainly, by replacing the nearest neighbor interaction by some prescribed adjacency matrix, you can certainly increase that to this kind of interaction as well. So the point is that these methods don't really, graph theoretic and network theoretic methods don't really care about what's sitting at the vertex. They're really just sensitive to the interactions and the topology of the interactions, and that's the power of these methods, as that I'd like to kind of exploit. However, I should say that one of the things that we're finding from a computational point of view is that in the Ising Hamiltonian, so there I have some spins, and the Ising model is typically next to nearest, it's typically nearest neighbor spins, but I can replace the nearest neighbor spins with some other adjacency matrix, and that'll tell me about how these spins interact across the network. And then I can try and calculate all these things. But it turns out that writing the Ising chain in terms of the Pauli spins is computationally much more expensive than making a Jordan-Wigner transformation and writing it in terms of fermions. So if you go to a basis of Majorana fermions, so if you go to the Majorana representation of the Ising spin chain, for example, you can double your Hilbert space more or less, and calculate things in a far more efficient way. So this is one of the things that we're trying to do now, is try and understand how to phrase these problems in terms of the Majorana representation instead of spins.
Okay, very interesting. Yeah. Ida, what's the question situation?
Okay, there is a question from Camille, and do you have some clues or evidences what small world networks could naturally exist in the matter physics?
You mean could exist naturally? Okay, I
yeah,
see, that's what you
I
said.
mean,
without the, so I'm not allowed to say Facebook, right?
No. No, but like I mean, you study quantum spin chains on the
Right.
small world topology.
Yeah.
Does it have any analog in reality or in the
Indeed it does. Okay, so the first couple of examples that I'm thinking about are all man-made, so I'm not allowed to quote those. But like I said in the beginning of the talk, the architecture of the brain seems to display, at least if you ask the right questions, small world interaction. So let me share my screen again, if I can. Sorry, where is this? All right, so I admit that I picked examples that are all man-made, except for this one. So this is a map of the architecture of the connectivity of neurons in the human brain, and there is some clues and evidence that that the architecture of the neural network in the brain is small world-like. That is not all. That is, it's more like the picture on the left-hand side than the picture on the right-hand side. Sorry, the other way around. It's more like the picture on the right-hand side than the picture on the left-hand side. So you have hubs that interact with each other. That's a small world architecture. So while it's not man-made, it's about man, but that's one. Watts and Strogatz themselves were studying synchronous systems, classical systems that synchronize. So birds that fly in these large groupings, or bees that swarm, or locusts that swarm, or fireflies that seem to fire synchronously. And the question is, how do you get synchronous behavior over such large systems? They're classical systems. They're certainly natural systems, but how do they synchronize? How do when you watch a swarm of birds fly, they behave as a collective rather than individuals. And the question was, how do they know how to do this? And it turns out that the interaction is more like small world interactions, that even though the neighbors, you only need to know about the neighbors, there need to just be one or two individuals that can see the swarm, and that determines the dynamics of the behavior. So this, it features prominently in the collective behavior of synchronization.
Okay. I think I'm a little bit concerned about the time, and I see our participants synchronizing away. Yeah. So Jeff, thank you so much for this really exciting talk, and for sharing a lot of connections that might not have been obvious to all of us. And we need to make a mental note to invite you again down the line in some time to hear how the story ends, yeah, or it continues. Of course, the story never ends. Yeah,
that's right.
So, thank you very much to everyone. Thank you, Jeff, again for offering your time and this very interesting material. Ilya, thank you for coordinating the questions. And let's just finish with two adverts. Tomorrow afternoon we have the third lecture in the mini school on practical quantum computing. So if you want to learn how to program IonQ, switch on tomorrow afternoon. And next week, Monday, we have another very interesting talk by Matthias Treuer, who is the chief quantum technologist of Microsoft, and he will speak about the future of quantum computing. Yeah, so I'm looking forward to see you again, some of you tomorrow and some of you on next Monday. So thank you very much. Have a good evening and keep staying safe, because level 1 doesn't mean that the epidemic is over. Yeah. So all the best. See you soon.
Thank you.
Thank you, Jeff.
Bye-bye.